So welcome back for lecture 4. In this lecture, we're going to transition from this 3-point form factor to 6 and 7 gluon amplitudes. I'll spend most of the time on 6 gluon amplitudes. And first of all, there's actually many similarities to the symbol alphabet between the form factor we discussed in the previous lectures and the hexagon functions, which describe the 6 gluon case. In fact, there are 9 letters, we'll see shortly, for the hexagon function space, and 6 of them are exactly the same as the form factor we just discussed, except, and those 6 were U, V, W, 1 minus U, 1 minus V, 1 minus W. The only difference is that W is now independent of U and V. As we were describing before, in the 6 gluon amplitude, the U, V, and W represent true cross ratios that have 2 Mandelstam variables in the numerator and 2 more in the denominator. We'll get to what the other 3 letters are shortly. But first, I just want to mention that now that we have a third kinematical variable, instead of having just a 2-dimensional kinematic plane, we have a full 3-dimensional space of kinematics. And as you might imagine, if you have 3 variables to play with instead of 2, there are a lot more different limits you can access, some of which have quite interesting factorizable behavior, which is somewhat different in each case. So one example, I mentioned that there is a Regge or forward limit in that Higgs or 3-point form factor, but it doesn't really expose the full richness yet that we can see in the case of 3 gluons. With 4 gluons, it would, but in the case of 6 gluons and no operator, the 6-point amplitude, there is a very rich structure happening already in a kind of forward limit, which is called the multi-Regge limit. In this limit, from the point of view of colliding particles, you have 2 very high energy incoming particles, say gluons, and in the final state, you have 4 particles, and those particles are supposed to have momentum transfer that is held fixed, but high energies or high components of the longitudinal momenta along the beam line, along the direction of the incoming particles. Now, furthermore, the longitudinal momentum or energies, or actually we call them the rapidities, are hierarchical. So 2 of the particles have very high rapidity, and their momenta is almost exactly equal to the incoming momenta. And then the further particles, in this case, just 2 of them, have correspondingly smaller energies, but they're still far from each other. So their rapidities, which is more or less the log of their longitudinal momentum, is hierarchically arranged, sort of like this. You can also look at this limit in terms of what the closed polygon looks like. And because 4 of the particles are have 2 equal pairs, it looks mostly like this. And then there's a small hook around the end represented by these guys with smaller momenta. Now, this limit has been studied for many years, and in QCD, it's sort of called the BFKL limit. And there's a kind of factorization that takes place where the factorization involves a ladder of what's called Reggeized gluons being exchanged in the T channel. And that leads to an exponential or a series of large logarithms in the perturbative expansion that can be resummed. And the factorization doesn't really take place in the original variables U, V, and W in this limit. Instead, it factorizes in a transform space, which can be obtained by a Fourier transform and a Mellin transform. And a lot of this has been explored over the years, and I don't have time to go through all of it. I'm just going to, again, kind of do it from a bootstrapper's perspective, is what does the boundary condition data look like, roughly? There's another factorization, which I won't even discuss in any detail at all, but just to let you know about it. Once you have 6 particles, you can construct a region where 3 of the particles have almost 0 invariant mass. You could do this if these 3 particles were all outgoing, but then they would be forced to be collinear, and that would be a triple collinear limit, and that would send other variables to 0. So it's a bit simpler to think of this factorization limit as a limit of 3 goes to 3 scattering. So 1, 2, and 3 are incoming, and 4, 5, and 6 are outgoing. So in this limit, 1 and 2 can scatter, and they can produce the real particle 6 and an almost on-shell particle that then collides with 3 and generates particles 4 and 5. So this 3 goes to 3 factorization is sort of a cleaner way to think about the multi-particle pole. And in this region, you're trying to sort of force all the virtual particles that connect these 2 blobs to travel in a small pipe, roughly, because the virtuality being exchanged here is going to 0. And it's not really a good idea to try to force colored objects into a small pipe, and therefore it's a heuristic reason for why the amplitude is suppressed in this region. It's suppressed by a log squared of delta, and there's actually a cusp anomalous dimension appearing here. This is a traditional Sudakov region, although it's Sudakov for a virtual amplitude rather than for a real process. So this delta then is the Mandelstam variable or kinematic invariant of 3, 4, and 5. And this can be studied to very high accuracy in planar n equals 4. Bernin and Chalmers studied the one loop behavior of factorization, and also looked at it with Matt von Hippel a while ago in some early studies in the n equals 4 theory. But this flux tube method, as described by Sever at a talk a few years ago, can be used to describe this particular limit. And of course, then you can check it anytime you have computed the amplitude. I should mention that the leading power behavior only occurs in the NMHV sector, although there's some subleading power behavior in MHV as well, in terms of the gluon helicities. Here's another limit you can access from the 6 gluon amplitude, and that's a limit where 2 of the 2 incoming partons almost break up virtually into collinear pairs, and then these pairs independently scatter into 2 additional pairs of gluons. So it's a 2 goes to 4 limit. There's also a similar 3 goes to 3 limit, but this is the 2 goes to 4 version of it. And it looks like independent scattering, 2 goes to 2 scatterings of 2 different pairs. So at the LHC, there are or at Hadron Colliders in general, there are searches for scatterings like this that come from 2 independent partons. And the characteristic feature is that these guys have 0 transverse momentum. And so the sum of the transverse momentum of 4 and 5 transverse to the beam is 0. And similarly for 1 and 2. But there's a region of single parton scattering, which looks somewhat like this, that can be explored. And it has singularities too, which are also Sudakov in nature. And furthermore, it has an interesting representation in terms of the Wilson loop. When you go through the analysis of this Wilson loop that corresponds to this configuration, you find that because leg 3 is approximately, the x and 1 minus x are approximately parallel, these lines rather, that this line here and this line here almost touch each other. So this subprocess, this 2 goes to 2 subprocess, is this lower one that is bounded by 4, 5, x, and y. And to the extent that these guys are almost on shell, then this becomes a closed Wilson loop. And so this variable z must be going to 0. So in other words, it's a self-crossing limit where the hexagon almost becomes 2 squares. This limit, by the way, overlaps the MRK limit, because if we go back to this picture, well, these don't have to cross, but because these guys are getting small, they're effectively almost crossing there. This is the limit of a very small box. So there's an overlap of the MRK limit, and you can apply results from one limit to try to connect to the other limit. The singularities, when you have 2 Wilson loops that cross, were studied a long time ago. There's a Wilson loop renormalization group equation, and some of that governs this behavior. So to sort of put together some of these regions in a single plot, we have these 3 cross ratios, U, V, and W. The multi-Regge limit turns out to be at this point 1, 0, 0, as we'll see a little bit later. But it's not on the Euclidean sheet. There is a Euclidean sheet where U, V, and W are all positive and where the functions are all real. But that's not the sheet that's relevant for 2 goes to 4 scattering or 3 goes to 3 scattering. For 2 goes to 4 scattering, you need to take U to 0, so sort of enter this plane and do an analytic continuation, which as U wraps around 0 in the complex plane. That causes all the functions in question to develop imaginary parts. And then you come back out and you approach various physical regions, which include multi-Regge. And then this self-crossing region turns out to lie on this line. As I mentioned, the 2 overlap, and that overlap is where this line comes down into this point. The near collinear limit, where the OPE can be established or can be checked or used as boundary data, are these green lines here. So there's a limit, V goes to 0, as we were discussing in the form factor case. U and W are generically independent, but in the near collinear limit, U plus W goes to 1, similarly to what happened in the form factor. And then these are related by dihedral symmetry. And then there are various other lines. This one is a symmetric line. And the multi-particle factorization limit, those 3 particle invariants appear in the denominator of 2 of the cross ratios. So that limit doesn't really appear here. Rather, it's out at infinity. So a little bit of history, that the 6 gluon amplitude was computed at 1 loop ages ago. And then about, I guess, 12 or 13 years ago, it was computed numerically in both the amplitude and Wilson loop pictures. And it was discovered, sorry, that should be 1465 or this one of these. Anyway, it was computed in both the amplitude and Wilson loop pictures, and was found that the remainder function agreed between the 2. So that was sort of evidence for a unique dual conformally invariant remainder function for this non-trivial kinematics. Then the Wilson loop picture was used to evaluate the entire expression analytically. And at first, this was in terms of a large number of weight for G functions. And then the symbol and this kind of coproduct type analysis terminating in the symbol was applied to that expression. And it was found that the whole thing collapsed to a very short expression, which could be written in terms of classical polylogs. In fact, most of these results can't be expressed in terms of classical polylogs, but the 2-loop answer can be. And furthermore, this symbol exposed of course, the symbol alphabet. This work by Goncharov, Spradlin, Vergu, and Volovich. So the symbol looks like this. And you might notice that, of course, as I was saying, it involves the same letters, U, V, W, 1 minus U, 1 minus V, and 1 minus W, and all permutations are applied here. But in addition, there are 3 more letters, YU, YV, and YW, which we'll get to in a second. Very curiously, if you set these terms to 0, this expression is the same as the previous expression for the 2-loop remainder of the 3-gluon form factor. So that's kind of a surprising thing, but it seems to be a total red herring, if you want. That is, at higher loops, now that we know both sides to higher loops, there doesn't seem to be any close connection between those quantities. But at 2 loops, it's actually the same, even though it may not look like it from this representation, because I've included different sets of permutations. So what are these variables YU, YV, and YW? They're not independent of the U's, because there are only 3 kinematic variables. They must be some functions of U, V, and W. And the functions look kind of ugly. They involve, so YU, you need to construct U minus Z plus over U minus Z minus. And Z plus and minus in turn involve the square root of a quantity delta, which is cubic in U, V, and W. So it has this quadratic term and then this last term. And so these quantities, though, can be written in a more natural way by introducing momentum twisters. I think you heard about momentum twisters from Jake Bergili, so I'm not going to really describe them in detail here. They're a way of solving the momentum conservation and on-shell conditions automatically, although they have a projective symmetry that needs to be taken into account. But they have a components, I, J, K, L, all label external states, this lower index, and A is a 4 component. And the only invariants you can build out of them are 4 brackets, where you contract 4 of them with this totally anti-symmetric tensor epsilon A, B, C, D. As I was saying, they have this projective nature, and therefore, when you want to find things that are projectively invariant, there are not as many quantities to write down as you might think. And there are essentially 9 of them. And those are shown here, and they are identified with the cross ratio U, 1 minus U, and YU. I've only shown you 3 of them because the other guys can be obtained by cycling the indices. So when you cycle I to I plus 1, you get the formula for V. When you cycle I to I plus 1 here, you get the formula for 1 minus V. When you cycle I to I plus 1 here, you get the formula for 1 over YV, because these guys are what we call parity odd, and they have sort of the full Z6 behavior of the hexagon. Whereas these guys, when you rotate, when you cycle through, they come back to each other after only 3. So there's a natural reason for these letters to appear in terms of the connection to momentum twisters. And that story and another story about cluster algebras, which I'm not going to go into, has been a very rich way of trying to understand what are the right variables for 7 point, 8 point, 9 point, and so on. And there's a lot of activity in that today. But for now, we're just going to take these variables as given and ask what other things do we need to do to find the correct function space for 6 gluon amplitudes. Well, the first thing we need to do, going back to the form factor as a guide, we were discussing its branch cuts and the fact that they only occurred when Mandelstam variables are 0, because all the internal particles are massless. Once again, those just correspond to regions where the cross ratios U, V, and W go to 0 and infinity. So we can never, and that limits the first entries of the symbols to be just U, V, or W. 1 minus U is not allowed, just as before. And also the Y variables cannot appear in the first entry. So furthermore, when we start talking about not just single discontinuities, But double discontinuities, we have the Steinmann relations. We discussed the Steinmann relations earlier, and the fact that they implied vanishings of double discontinuities of amplitudes suitably normalized between two different three-particle invariants. For example, we argued that the BDS-like normalization, because the thing divided by doesn't have any three-particle cuts, it has the property that the discontinuity in S123, and then take the discontinuity in S234, vanishes. So the question is, what does that imply for discontinuities in terms of conformally invariant cross ratios like UV or W? Well, it's better not to use UV and W because they each contain, they're tangled up. In terms of the Mandelstam variables, they have two different three-particle invariants in them. So it's better to take ratios. So if we take a ratio of U and divide by V and W, you'll see that the S123 here will cancel that S123. And the S345 will cancel this S345. And all we'll be left with is a pair of S234s in the numerator when we divide U by V and W. So just to say that again, coming back to here, this quantity U over VW, which we were calling A before in the form factor context, and we'll call it A again, it has S234 squared, and it has no S123, and it has no S345. It has a bunch of other terms, but they only involve the two-particle invariants. And so this A isolates one of the three-particle invariants, and then B and C contain the other two. So once we've isolated the three-particle invariants in these letters, then it's easy to state that the consequence of this vanishing in terms of these non-dual conformal invariant letters is simply that these dual conformally invariant double discontinuities should vanish, plus all dihedral images. So that means that at the level of the symbol, A cannot appear next to C, and by dihedral invariance, it can't appear next to B either. So so to just recap what we found, the Steinmann relations, when promoted to relations among dual conformal invariant objects, say that the discontinuity in B of the discontinuity in A should vanish. That corresponds to clipping off the letter A first, and then the letter B in the symbol. That's how you extract this double discontinuity at symbol level. So if A is followed by B and is followed by anything else, those should all vanish, plus the 5 other dihedrali related conditions. Now, amazingly, in the symbols for the 6 gluon amplitudes in this BDS-like normalization, well, not only was that seen, but also it was seen at any point in the symbol. So even if A and B did not appear at the beginning, but just in the middle, they were. It was found that this adjacency constraint held. And one interpretation of that is that the Steinmann relation should hold on arbitrary Riemann sheets. And the basic idea is that you can get from one Riemann sheet to another by moving across some other discontinuity, taking a discontinuity in some other variable out here, not shown. And after you've moved to another sheet by shifting it by a discontinuity and clipping off arbitrary stuff in the symbol, then you apply the Steinmann relations once all these things are removed. So that's a kind of heuristic justification for why you might impose these conditions in the middle of the symbol and not just at the beginning. I should say these relations have also been interpreted mathematically in terms of cluster algebras and certain adjacency properties. And that was worked out by Drummond, Foster, and Gertigan, and there have been a number of additional papers investigating this, both for the 6-point case, 7-point case, and beyond. So when you impose these conditions, these 6 conditions, and you build up the space iteratively from from the beginning, also imposing the first entry branch cut condition, you find that the space that you construct only has 40 of the possible 9 times 9 or 81 pairs, 9 because there are 9 letters. So you might have thought there were 81 minus a certain set of integrability relations, which turns out to be 26. That would have given you 55, but actually only 40 appear. So these extended Steinmann relations together with the first entry relations are quite powerful. And by the way, you can impose this 40 pair relation, and you can ask how many independent triples are there. And then you can go count triples in the symbols of these explicit amplitudes. And you find that they saturate the triples. In other words, unlike the form factor case, there are no additional triple relations. When you build up the space of hexagon functions at symbol level, order by order, using these rules, that you have a first entry condition and 40 pairs and nothing else, this is the dimension that you find. Actually, that's not quite true. There are some other conditions that are a little subtle involving zeta values that cut these down, but not by very much. So it's approximately a correct statement. So the number of symbols that you find in this hexagon space defined this way includes 3, log U, log V, log W, or log A, log B, log C. There are only 6 functions that survive the Steinmann relations instead of 9. And that 6 is already telling you that the growth is going to be slower in this space. And indeed it is. By the time you get to weight 8, there's almost a factor of 4 between these spaces. And so this one grows quite slowly and can therefore be constructed to quite high weight. On the other hand, the multiple final entry conditions aren't really understood as well. And when I say understood, I mean empirically. To illustrate that, I want to show the same table I showed in the last lecture for the form factor space, which we now have the numbers through 8 loops, and a similar table for the hexagon function space. Now, the hexagon function space table is slightly different. You'll notice that it starts with 6 each time, except for 2 loops. And the reason is that we now have parity odd functions, and there's basically a 6 vector of independent functions. Actually, this should probably be 5. Okay, I'll fix that later. So no, sorry, it's 6. It includes MHV and NMHV both. So there are 6 transcendental functions at weight 2L, and we apply the same procedure that we applied before. We take coproducts, we figure out how many independent quantities there are, and we keep iterating to the left. And at some point, we hit saturation in that the number at a given weight is what we saw before. And just as in the form factor case, we make the number green then, and we say that it is saturated. And over on the right, we declare saturation if the number was the same as it was 1 up and 2 over, because that corresponds to a saturation of multi-final entries. In fact, we get very little saturation here. These numbers only stabilize at the double final entries at 7 loops. So it takes a long time compared to what happened up here. On the other hand, the saturation on the left is much more quick. And so by 7 loops, we've already saturated out to weight 7, whereas we were stuck over at weight 5 or so in the form factor case. So this is the sort of general structure of this space. It grows more slowly from the left than the form factor space, but you don't have as much information about the final entries coming from the right. So as I was mentioning before, in the case of 6 gluons, there's not just one amplitude to construct, but there's a sort of a set of amplitudes. In fact, there's MHV and NMHV. Now, the MHV amplitude, that is really dual to a bosonic Wilson loop, which is this path-ordered exponential around this closed light-like contour. And that goes hand in hand with a certain supersymmetry Ward identity, which I mentioned in the first lecture. That Ward identity, which says that the amplitude divided by this spinor bracket ij to the fourth has no knowledge of where I and j are, that implies a dihedral invariance of the amplitude when normalized by the tree. And in fact, this quantity is closely related to E, a transcendental function. And this dihedral invariance implies that E6 of U, V, and W for the MHV amplitude is totally symmetric. The NMHV amplitude, in contrast, is a quantity that should be decomposed over, it's not really a scalar in superspace. The MHV amplitude has a very simple structure in superspace. It's basically a delta function. But the NMHV amplitude has an additional, more complicated delta function that appears, and more of them. So these dual superconformal R invariants, or 5 brackets, they contain all of the rational structure in the NMHV amplitudes, whereas in the MHV amplitude, they're all proportional to the MHV tree. So without going into a lot of detail, these 5 brackets that depend on 5 of the 6 variables, they can be written in a shorthand, which just introduces the 6th variable. So A, B, C, D, and E all have to be different for this to be non-zero. So if they're all different and there are only 6 arguments altogether, you might as well replace it by the 6th one. So then you can write it with just a single index in parentheses like this. So there are 6 of these quantities. They're actually not quite all independent. There are some relations that 3 of them add up to the tree, like 1 + 3 + 5 or 2 + 4 + 6. But when you represent the NMHV amplitude, you can look at what parity does to these R invariants. And once you've identified that, you can recognize that there's a parity symmetry, and these coefficients, which we call italic E, not to be confused with curly E for MHV, these 3 components are the parity even pieces of the NMHV 6 gluon amplitude, when we've normalized by the same BDS-like function at MHV. And the reason, of course, for doing that is so the Steinman relations will hold for these quantities, E and E tilde. E tilde is the parity odd piece of the of that NMHV super amplitude. So you can see that both E and E tilde appear in 3 different permutations. Now, actually, because of the identities among these R invariants, these 6 functions aren't all independent, or in particular, the 3 E tildes are not independent. And it's possible to choose the cyclic sum of this plus this plus this to equal 0 as a kind of gauge choice. So there are really 5 independent functions in NMHV. And then there's the MHV answer, curly E, to give 6 functions altogether to determine from weight 2L at L loops. Now let's talk about constraints. At least for the MHV case, the constraints are very similar to the form factor that we just discussed. There's a total dihedral symmetry. There's a well understood collinear limit. There are various discontinuity constraints. And in addition, there's a multi-Regge constraint. And that was worked out in steps by various groups, but to all orders by Basso, Carenhua, and Sever as an analytic continuation from the flux tube OPE picture. And this multi-Regge constraint is technically easier to impose than the OPE from a bootstrapping perspective, because it governs functions that are at leading transcendentality, while the OPE constraints involve functions that have transcendentality drop and lead to more complicated functional behavior. We saw in the form factor case that the near collinear limit involved rational functions multiplying the harmonic polylogs. And at high orders in the OPE, that gets rather messy, especially when you're still trying to fix a large number of parameters. So this multi-Regge constraint is just a little easier to impose because it's governed by a limited set of transcendental functions with no real growth in the rational function behavior. To be more specific, if we go into the 2 goes to 4 multi-Regge limit in the 6-point case, that when you work out what this kinematics corresponds to in terms of the dual conformal cross ratios, you find that U goes to 1 in this region and V and W go to 0. Now that is actually an endpoint of 2 collinear lines. We call it a soft limit. And the remainder function would vanishes in all the collinear limits, just as it did for the form factor. And so it would also vanish in the soft limit. However, there's a distinction, which is that we're not taking this limit in the Euclidean region, but we're first going to go into a physical region. And so, as I was mentioning earlier, you first need to analytically continue U around the origin by wrapping U goes to U e to the minus 2 pi I. And then you need to come back out and transport that point back out to this. And at that point in the physical region, you get non-trivial dependence on various ratios that are held fixed in this limit. So the limit should be applied with V going to 0 at the same rate that U goes to 1. And so this should go to some fixed quantity, which is traditionally called 1 over 1 minus Z magnitude squared. And W goes to another limit, which is Z squared over 1 over 1 minus Z squared. If you go through the analysis of what the letters of the symbol become when you take this limit, you find that they become just Z's and 1 minus Z's, and Z bars and 1 minus Z bars. And there's also a further constraint that the first entry coming from U, V, and W should only contain Z squared or ZZ bar and 1 minus Z, 1 minus Z bar. So that space of functions, apart from the divergent parameter 1 minus U, that space of functions is called single valued multiple polylogs or single valued harmonic polylogs, and was first described by Francis Brown. And so all of the functions, the amplitudes, for example, the remainder function, can be expanded in terms of such functions of very weight going up to 2L minus 1. It's 2L minus 1 because there's a loss of 1 weight from this 2 pi I, which comes from taking a discontinuity. And there's also, for high values of R, those will be at lower weight because of these powers of logs of 1 minus U. So there are a set of functions here that can be constructed from a multi-Regge prescription and also serve as targets for ansatz in the same way that the near collinear limit provided constraints. The master formulas for this behavior were written down how the amplitude should factorize were written down by Fadin and Lapatov a while ago. And another formulation was given by Karen Hua. And then the quantities that appear in this were computed by Basso, Karen Hua, and Sever. And so basically the MRK limit of the remainder function, or something that's actually closer to the curly E function for MHV, has a particular form in terms of quantities, which I'm not going to completely define, but I just want to show you its rough structure. It has a integral over nu, which is a Mellin transformed variable, and it also has a Fourier transform involving the phase of W. Traditionally, W was used, but it's just the negative of Z. So the phase part is the Fourier sum, and this is a inverse Mellin integral. The NMHV structure is almost exactly the same in terms of the same basic sums and integrals appearing, but the integrands are slightly different. I should have mentioned that this is the BFKL trajectory, omega of nu and n, and it multiplies a large logarithm, which is buried in here. So if you rewrite this as the exponential of omega times the this logarithm, you'll see there's a large logarithm of as u goes to 1. And this is just a shift of variables between two different conventions. So this is sort of the BFKL ladder description and summing up a large set of Reggeized gluons. And then those gluons interact with something at the top or the bottom of the ladder. And the product of those two things is called the impact factor. And it's given here, this phi reg. And there's a similar one in the NMHV case, which is quite closely related to it. And it could be, these extra factors also differ slightly, and they could have been absorbed into these impact factors phi. So that's the rough structure. You can evaluate these integrals by closing contours and summing over residues. And so you have various double sums to do. And they basically all turn into these single valued harmonic polylogs in the end. So if you are able to do those sums and identify them, then you can work out the behavior of the remainder function and of the ratio function involving NMHV in terms of quantities like this, where these G's and H's are all single valued HPLs, as are the P's and Q's. In the NMHV case, there are additional factors which you can think of as coming from the limits of the dual superconformal invariants, these R ratios. So when you carry out this exercise from the bootstrap perspective and take the limit, you can compare the results with those of Basso and Karen Hua and Sever. And you find that the BFKL eigenvalues, which were called omega here, and they can also be redefined in terms of a quantity E. It's another way of expressing them. Anyway, they agree perfectly through very high orders. And similarly for the impact factors, both for MHV and NMHV. And all of these quantities in the Fourier-Mellin space are just linear combinations of psi functions or logs of gamma functions and these simple rational building blocks. But of course, they get very complicated at high weight. So all of that was just to say that we have a multi-Regge kinematics where we can also apply constraints. And we like to do it before we get to the OPE constraints, because these are just messier. And when you're getting to very high loop orders, keeping things simple is of the essence. So these tables are meant to be the analogs of the tables of parameters I showed in the form factor case. One difference is that now we have MHV parameters for curly E on the left of the parentheses, and on the right we have the ones for the NMHV functions, which get determined together, these E's and E tildes. So there's a list of all functions, and that just corresponds to the number of functions. And in this case, it's functions, not symbols. This would be the total number of functions in the space. And on the left, there would be the number of parity even functions, because we know that E is parity even. Anyway, once you've imposed various other dihedral symmetries, the numbers drop by a large factor. And then you can impose a final entry condition, which actually follows from the Q-bar equation in this case. As I was mentioning earlier, there's a similar one for NMHV. And at this point, you're down to dozens of parameters, well, a bit more at 6 loops. And then when you impose the collinear limit, now you're down to handfuls of parameters. And at this point, you can start imposing the MRK limits. And fairly quickly, the answer gets determined, except for the MHV 6-gluon amplitude, which survives all of the multi-Regge constraints. And the 7-gluon MHV amplitude is the same, whereas the NMHV ones are completely fixed before you even enter the OPE limits. But this one, for this one parameter, he's a pretty fiendish function. Not only does he survive the entire MRK limit, but he also survives all the terms in the OPE expansion at leading order. In the hexagon case, the expansion parameter is really t and not t squared. And there are t to the 1 terms in the OPE, which all work out perfectly. And here they even allow this one parameter to survive. But when you get to the t squared terms, you can kill it off. Now, we've also inspected behavior of these functions at another point we call the origin. I'm not going to get into detail there, but that's another way of killing off this guy, is by inspecting the behavior of the MHV amplitude at the origin. Anyway, the upshot is that by applying these various constraints, the amplitude is uniquely determined. And we didn't need to use very much of the MRK limit in all cases except this one. And in fact, you could say that we could self-consistently determine all the terms entering the MRK limit order by order, because by the time we get to here, we've determined a certain number of subleading logarithms, which is enough to fix the answer to the point at which these are zeros. These asterisks, I'm not going to explain here. They have to do with certain normalization factors and assumptions about that. Now that we've got the amplitude completely fixed, we can do the same thing we did in the Higgs case, in the form factor case, and we can plot it along various lines where it simplifies. One line on which the symbol on which the function simplifies is this line here, where we set v equal to u and w equal to 1. In that limit, the symbol collapses, the symbol alphabet collapses to have just 2 letters, u and 1 minus u. And we know immediately from that that the answer should just be harmonic polylogs with just zeros and ones. So at most 2 to the 14th of them, which is a small number compared to 3 to the 14th. So anyway, this is a simple line on which we can extract the answer by writing in terms of HPLs and then Taylor expanding around various regions. And when we do that, we find that the functional behavior tends of one loop order divided by the other flattens out. And this is a feature of this finite radius of convergence, we believe, in that the limit minus 16, which is the ratio for the cusp anomalous dimension, is generically being approached for generic values of u that are not too big and not too small. We also see these spikes here, but this is just because this function crosses 0 at some point. And while it's generally pretty proportional to the previous function, the zero crossings aren't always exactly at the same point. And then you get a zero when it's in the numerator and an infinite spike when the zero crossing happens a little bit later in the denominator. So this generally supports the picture of a consistent finite radius convergence that may be equal to the cusp. Of course, it hasn't reached this value yet, but if you look at the cusp anomalous dimension and take ratios of successive orders for it, it's not too different from these values. At very small u, you're approaching the soft or OPE corner, and both numerator and denominator have some log divergent behavior, and that's all you're capturing there. And over here, the quantities I think are all going to a constant, but the constant doesn't seem to be closely related in its ratios to -16. Since we also have the NMHV amplitudes, we can look at ratios of them and we find a very similar picture going on. If u is very small or u is very large, we can get divergent behavior, which is logarithmic and varies from loop order to loop order. And so you get big differences. But when you're in the bulk where u is of order 1, so that would be where log 10 of u plus 5 is around 5, just to shift things out here, you get this kind of flattening of the curve to that value. We also can look at NMHV parity odd. In this case, we plotted the ratio function, which is defined as the ratio of NMHV over MHV. And in this case, the parity odd part is denoted with a tilde. This guy is vanishing on the previous line, UU1. This line, by the way, is a permutation of UU1, just to illustrate a different region. And this one vanishes on UU1. So we go to another line, which also has this nice HPL property, U11. In this case, we chose to normalize the answer. There wasn't a great way to normalize it by a fixed quantity. So we normalize it by the coefficient of log squared u in the u goes to 0 limit. But when you do that, you see that the shapes are very similar. They lie almost on top of each other for moderately small u, and they just tend to fan out at larger values of u. So again, generically, shapes are very similar from one loop order to the next for generic values of u. So now in the few minutes left, I'll just give a quick mention of the situation beyond 6 gluons. So the cluster algebras, which I haven't really gone into, have been used to provide strong clues as to what the right polylogarithmic function space is. In particular, there's a there's a symbol alphabet that was discovered by thinking about these cluster algebras. And that symbol alphabet has not 9 letters, but 42 letters. And it was first used to bootstrap the 3-loop MHV 7-point amplitude. And in fact, it was surprisingly rigid in the sense that once this alphabet was specified in the first entry conditions, a function that was found that had the right dihedral symmetry without even needing to apply any OPE or multi-Regge constraints. Now, this was done before the Steinmann relations were applied, but with the Steinmann relations and the existence of a suitable ansatz that didn't have any 3-particle invariance, one could trim the space down further and go to 4-loop MHV and 3-loop non-MHV. And then including also the extended Steinmann relations, the 4-loop NMHV could be bootstrapped. Now, this original bootstrap was done at the level of the symbol. And then last year, my student Andy Liu and I were able to lift the symbols to actual functions. So this is the alphabet that is used to describe the heptagon functions that enter the 7.7 gluon amplitudes, both MHV and NMHV, in planar n=4 super-Yang mills. And these are once again 4 brackets involving the 7 momentum twisters. And in some sense, these sets of 4 brackets from A1 to A4 look very similar to the ones that appeared in the hexagon case. However, the heptagon case also includes numerator factors shown here in parentheses that are not single products of 4 brackets, but involve non-trivial combinations that can't be reduced to these by certain identities or anything, Plucker relations. Anyway, these independent ones, this shows 6 of the 42 letters, and the rest of them are obtained by cycling I goes to I plus 1 mod I to get the rest. You can also construct these spaces, and this is a enumeration using the Steinmann conditions, but not the extended Steinmann conditions. And these spaces at various weights were enough to get the symbols through 4-loop MHV and 3-loop NMHV. And then applying also extended Steinmann to shrink these numbers down a bit further, 4-loop NMHV was bootstrapped. And as I was saying before, very little boundary data was needed at symbol level. Essentially, just that the collinear limits were well defined and not even really what they became in the collinear limit. Now, to go beyond the symbol and bootstrap full functions, it's useful to have some kind of a crutch where you can get around and move data about constants, because to get full functions out, you need constant information and you need to carry it from place to place. And there's a surface that Andy Liu and I found called the CO surface, which interpolates between various soft limits and also an interesting region called the origin. But for the purposes of the bootstrapping, the most interesting thing is that you have lines within this surface in which momentum becomes soft, and you approach the 6-point kinematics, where you understand everything that's going on to fairly high loop order. And it goes on to a limit where the 6-point kinematics has 2 very small cross ratios and 1 generic one. And then you can also go to the limit where U goes to 1 as well. Now you take all 42 of those letters and you take them into this surface, which is defined by having U3 and U4 generic, and these U's all very small, and U7 goes to 1. And when you do that, you find that the symbol letters, the 42 letters, collapse to something very simple. And in particular, you recognize that this is HPLs with 0s and 1s in U3, and this is HPLs and 0s and 1s in U4. And then these guys are small, so you can only get logarithms there. So that's what this function space is. And so that allows you to move around very easily on this surface because the function space simplifies so much. And in general, this CO surface looks very much like 2 copies of this line that shows up in the 6-point case. And in some regions, it approaches that line. And furthermore, the dihedral symmetry acts very nicely on this space. You can do a flip that moves you in this direction. And when you cycle by 3, you end up with another copy of the CO surface. And this point touches this point. And that is very useful because you need to be able to carry constants from one surface to its image. So you get sort of these petals, these CO surfaces, the dihedral images of them touch it at points, sort of like that. But of course, inside a 6-dimensional space. So that is can be used to carry out this bootstrap. Now, what is this surface? Well, it's a particular way of scaling the variables. We use a parametrization of the momentum twisters. There are 4 component twisters and there are 7 of them. So this is a 4x7 matrix. And it was parameterized in terms of generalizations of these T and S variables that we discussed in the form factor case. And in the 6 gluon amplitude, there's also an azimuthal variable F. And in the 7 gluon case, there are 2 copies of them. So there are 6 variables altogether. And you can use various methods to parameterize the 7 momentum twisters like this. And then every 4 bracket and every letter of the 42 letters can be written as functions of Fi, Si, and Ti. So to go into this limit or other scaling limits, you just apply certain scaling transformations. For example, to go to the OPE limit, you scale T1 and T2 to 0 with a common parameter. And that's the OPE limit for the heptagon, which actually involves two T's going to 0. There's another limit called the double scaling limit, where you scale the T's to 0, but you scale the F's in opposite direction. And then the CO limit is yet another scaling limit where you apply this transformation. In fact, you can investigate similar limits for n greater than 7 as well, which is something we're working on. Besides having this CO surface to move around, you also have branch cut conditions. They're very similar to what we had before. They end up only allowing certain set of the A letters in the bulk to be there, but we also need to impose branch cut conditions at function level for the on the CO surface. So on the CO surface, the branch cut conditions turn out to be enough to fix all of the functions. So what we can do is we require that a logarithm here of 1 minus U7, which is going to 0, that should vanish on the entire surface. That's a consequence of the branch cut conditions in the bulk. We also should not have any logarithms of 1 minus U3 or 1 minus U4 when we go into the appropriate points. And by applying these various branch cut conditions, along with integrability and the extended Steinman relations, we're able to fix all of the zeta values that don't show up at symbol level, but have to be fixed at function level. And so we can fully define the heptagon functions through their values on this CO surface. Now, in doing this, we benefit a lot from the fact that the space is already understood at the symbol level. So we are sort of tacking on a smaller number of functions, the ones that are beyond the symbol, and we're fully defining the symbol level ones. But the biggest matrices that are involved are the ones that are sort of symbol to symbol that were already known earlier. Having lifted these symbols to functions, we now can plot them. And so, for example, we can plot the ratio of the remainder function at L loop to L minus 1 loop on a line which is symmetric and as symmetric as you can get. There's actually a gram determinant constraint on the 7 different cross ratios. So they're not all independent. There are only 6 independent variables. In particular, if we choose the first 6 to all be equal, the 7th one is constrained to have this kind of ugly form. But in any case, this is a legitimate kinematical line that's about as symmetric as you can make it. And we can plot the remainder function on that line. And one of the interesting things is that when we do that ratio at 3 loops and compare it to the ratio at 4 loops, it doesn't look like it's going to minus 16. So obviously we need 5 and 6 loop information to know for sure. But we don't have that yet. We can also take the logarithm, though, of the, instead of the remainder function, we can take a closely related quantity, the 7-loop E function. And in this case, when we do make the similar ratios, the trend seems to be in the right direction. So at low loop orders, it depends a bit on what you plot. We can also plot the remainder function on 2 lines that go through a surface, which is the Euclidean version of the self-crossing kinematics that I mentioned earlier. And we find this similarity in shape. Whenever you have something which is kind of constrained to go to various limits, like 0 in this limit, and it has to go to the 6.111 value at this limit, you tend to get very similar shapes going on. So that brings me to the close of these lectures. I hope I've convinced you that bootstrapping is a very efficient way to get to high loop orders when you have enough understanding about the function space and the various kinematic limits in order to constrain all of the parameters. And once you have the results, you can explore them in various limits, such as the high energy or Regge limit, factorization, self-crossing limits, and a number of different pieces of information can be extracted. There's a great synergy with these OPE methods, flux tube OPE methods, involving the pentagon transitions and these additional form factors. So as I was mentioning, there's a rich set of agreement between the two. When you expand the FFOPE and the coupling, and you expand the bootstrapping results in the kinematic limit that's relevant, you get many very complicated expressions that agree exactly right on the nose. So in fact, the perturbative information also has aided in the construction of this very recent F form factor transition F3 beyond the leading order. Now a huge set of open questions are left behind. One is that if you can get to such high loop order, why can't you get to finite coupling? So we need to determine what the right finite coupling functions are. There are probably clues lurking in their OPE expansion and the kinds of functions that show up there, but maybe there are certain types of more complicated functions waiting to be defined that can lead to a bulk description at finite coupling, which was that holy grail I sort of indicated earlier. Another important question is whether this principle of maximal transcendentality applies to F3 beyond 2 loops, for which we need some QCD results. Another question is whether all of these techniques can be applied to other contexts, of course, more complicated kinematics in planar n equals 4, and eventually to QCD, and find out what we can learn about other theories, such as QCD beyond planar n equals 4. So that brings me to the end of lecture 4, and I hope you've enjoyed these sets of lectures. Thanks a lot for your attention. Bye.